In previous modules, we have mentioned several times the problem of storaging of data. Welcome to Module 10, Audio Coding. In this module, we will explore how digital audio is compressed and encoded, balancing storage efficiency with sound quality. These concepts are foundational for understanding modern multimedia technology. Digital audio is stored, managed, and transmitted in various formats, as we have seen. The audio coding format determines how data is structured, whether uncompressed or compressed. Compression makes files smaller while maintaining how much quality as possible, enabling efficient storage and streaming. Audio coding, as you can imagine, has several benefits, such as reduced file sizes and efficient transmission for networking, which saves storage and bandwidth. Some of its application includes, for instance, coming from our daily life platforms, streaming platforms. Services like Spotify, Apple Music, and YouTube rely on audio coding to compress audio for efficient streaming while maintaining good sound quality. Or telecommunication technologies like VoIP, like Skype or Zoom, and cellular calls like 4G or 5G. They use basically audio codecs to transmit voice over networks with minimal delay and bandwidth usage. In this kind of application, I would like to mention that the greater is the size of the file and the slower can be the transmission of the data, as you can imagine. Another field of application is film and gaming. In movie soundtracks and video games, audio coding ensures immersive audio with surround sound like Dolby Digital or DTS, while optimizing storage space. You can understand that when we have multiple channels, like in surround sound systems, the storaging effort increase exponentially. Among possible applications, we delve into some main use cases. The first is coding for storaging, which is the easiest one. In this scenario, audio source is coded mainly to optimize the storage effort. It does not have any particular real-time requirement. For this reason, it does not offer any transmission or optimization. An example of it is the recording and storing for an audio source for later elaboration or listening. For instance, if we would like to record our music and we store it for listening later on in MP3 file. A second scenario is coding for real-time transmission. So in this scenario, the audio source is not thought to be stored, but rather transmitted in real time. Hence, the coding procedure should be optimized for minimal transmission delay. An example of this application is the VoIP or networked music performance. The third scenario, which is the most complex, is the coding for streaming. In this scenario, the audio source is first stored and then later on transmitted. For this reason, the audio coding procedure should be optimized for both storing and transmission. In order to be effective, two different audio coding procedures are often applied. An example of it are DSP streaming services like Spotify, Apple Music, or YouTube as well. Let's delve now into typologies of compression audio coding or uncompression audio coding. So, uncompressed audio retains all the original data with no size reduction, so just coding. The most common method is pulse code modulation, PCM. Maybe you have heard about it, which convert digitized audio into binary code. Stereo signals here are either in interleaved format that alternates data for multiple channels, or planar format that groups data from the same channel, as we can see in the figure. Let's move now to the compression procedure, which are more interesting for our case. So, compression procedures aim to first remove redundant or irrelevant information, such as frequencies inaudible to human or masked by louder sounds. We will see it. Second, to exploit the psychoacoustic model to identify the most important and prominent sounds to human perception and allocate more bits to encoding such sounds. The remaining sounds are either encoded with fewer bits or discarded altogether. This procedure allows to represent the audio in a more compact form. Finally, the third, applying advanced techniques like quantization and entropy coding. So compression can be lossless, for instance FLAC format, which perfectly reconstruct the original data but has lower compression rates or risk to have lower compression rates. And then lossy, like for instance MP3, which achieves higher compression by approximating original data with some quality loss. Let's now move more in deep into the compression steps. The first step is try to remove redundant information. Redundant information in audio can be reduced by, for instance, first, exploiting the non-uniform distribution of amplitudes. Most audio samples, in fact, especially human voice, appear more frequently at lower amplitude levels. We can use less bits for the amplitude quantization for this kind of signals. Or another way is to exploit the correlation between sample values by storing differences between consecutive samples instead of absolute values. Or another one is to exploit the correlation between signals periods, storing only active frequencies at given time. The last, eliminating silence and leveraging long-term correlation between samples. Another kind of redundancy that we can remove in the compression procedure are those based on frequency. Frequency domain techniques focus on, first, removing not much used frequency bands, often in high frequency ranges. The long-term analysis of the spectrum might indicate that some frequency bands are not so much used in that signals, and thus can be removed. Second, provide priorities to frequencies with clear peaks, as these are more informative and critical for the perception. This is done by performing short-term power spectrum density. So, conclusion. In this lecture, we have explored the basics of audio coding, from uncompressed PCM to compressed formats like MP3. Understanding this principle is crucial for efficiently managing audio in modern applications, from streaming to gaming. Next module, we will continue on compressed for audio. Thanks for your attention.